Next topic is mobility of charge carrier. So what is the mobility? So we have understood that if you apply an electric field across a conductor, these electrons collectively will start moving. So the mobility of the charge carrier is drift velocity of these moving electrons, drift velocity, and for a unit electric field, drift velocity acquired by 1 unit electric field. Very simple. So mobility is written as mu. Mu is equal to Vd, drift velocity over unit electric field or 1 unit electric field. Now mu is equal to Vd by E. Now E can be then rearranged from this expression because Vd, drift velocity, is equal to Qe by m into tau. So drift velocity can be written as Q tau by m. Very simple. Then next topic is temperature dependence of resistivity. So we have already understood that the resistivity of a conductor depend upon the relaxation time. Okay, we have understood this. We have understood that if this relaxation time decreases, then this resistivity value will increase, and so resistance will also increase. Simple. How this can decrease, how relaxation time can decrease? Because of increase in the temperature. Increase in temperature. If you increase the temperature, the thermal velocity of these electrons will increase. Thermal velocity will increase. We have discussed this in detail. And so the relaxation time will decrease and resistivity will increase. Now, how much the resistivity will going to increase in metals? We are going to primarily discuss about metals. So metals, what happens? If you want to understand in detail, you can read this through. That for metals, the number density n of free electrons is almost independent of temperature. As the temperature increases, the thermal speed of the free electron also increases, and also the amplitude of the vibration of metal ion increases. The free electron will collide more frequently with metal ion. So tau decreases. So we have understood this in detail. So the relationship with the resistivity of and temperature is this. Resistivity at a certain temperature. Resistivity at a certain temperature, rho, is equal to the resistivity at T naught. Now, what is T naught? Okay, T naught. What is T naught? So don't get that T naught is equal to 0 degree temperature. No. Okay, T naught is the lower reference temperature. Lower reference temperature means, let's say you know the temperature T naught value for you is maybe, let's say, 40 degrees. So at 40 degree, you know the value of resistivity. If at 40 degree you know the value of resistivity and I ask you to calculate for 80 degrees, then you can take the 40 degree, this value as T naught, the lower reference temperature. Okay. So the lower reference temperature is not 0 degrees, it can be any value. And this alpha, this value here, alpha is the coefficient of resistivity, thermal coefficient of resistivity. So this value is more important. The temperature coefficient of resistivity, thermal coefficient of resistivity, all are same. Increase in the resistivity per unit resistivity per degree rise in temperature. Okay. So be very careful with the formula here. So resistivity at a temperature T, this value here is equal to resistivity at any lower reference temperature, and then 1 plus alpha change in the temperature T minus T naught. Okay, T minus T naught. So from this expression, you can deduce that alpha will then become change in the resistivity. It will become change in the resistivity. over original resistivity times change in the temperature. Okay, this value here times change in the temperature. Now, then this whole expression can be then written as alpha is equal to 1 over alpha is equal to 1 over the original resistivity times change in the resistivity by change in the temperature. So you will get numericals based upon this particular formula quite a lot, where resistivity at a lower reference temperature is given, this value is given, and this value is supposed to be found out, the rate of change of resistivity with respect to temperature. Then this value of alpha, that is this temperature coefficient of resistivity, this is not always a constant. In this expression it seems like always constant, but it is not constant, because this value can change. It depends upon the material. So in your NCRT also you will find this graph, and this is the graph representing the resistivity value of copper. Okay, resistivity value of copper, so this is copper, and with resistivity value for nichrome. So this is for nichrome. As you can see, this copper resistivity graph with respect to temperature changes. So at low temperatures, it is has different value, but then it rapidly increases. So we can figure out that this resistivity value is quite material dependent. Which material you are using? It is not. It does not show any common behavior. More detail about this is also given in your NCRT book. You can refer to the NCRT, and in NCRT this topic is discussed in detail. Please go through that. So as you have the relation for resistivity, okay, and in this relation you have this alpha. So you will also have a relation between resistance, okay, and you will get numerical based upon this formula as well. This is also a very simple formula here. Resistance at any temperature T will be is equal to resistance at 0 degree 1 plus alpha T. Okay, it's very simple. Now, as we see that this resistivity, we see that this resistivity, this copper and nichrome, they show very different behavior. Now that means if they show different behaviors, you see the resistance of the copper will not be increasing at the same rate all the time. So the rate of increase changes, the slope of this curve you change, but then you find that this nichrome is a straight line. That means this Ohm's law, because if the resistivity changes with respect to temperature, that means the resistance will also change, and then the Ohm's law is not valid all the time. Okay, it is only valid under certain condition. You see, the Ohm's law is obeyed by many substance only under certain condition, and one of the primary condition to be is temperature constant. Okay, temperature constant, it has to be a constant, then only this Ohm's law is followed. So it is not a fundamental law of nature. Ohm's law is not a fundamental law of nature that is followed under all circumstances, and that is the reason why we have ohmic conductors and non-ohmic conductors. So ohmic conductors would be the one that follows Ohm's law. Okay, ohmic conductor will be the one that follows Ohm's law, and then you will have non-ohmic conductors which will not follow the Ohm's law. Very simple. So Ohm's law conductors will always have graph which is a straight line. The VI graph, voltage current graph, will be a straight line. Or current voltage graph, whatever graph you get, it will be a straight line, because the straight line would represent R, current, resistance. It will represent resistance, and resistance is constant at a constant temperature. So Ohmic conductors are those which the graph will be a straight line. Non-ohmic conductors, graph will not be a straight line. It can be very different. For semiconductors, it is different. For different electrolyte, it is also different. Non-ohmic conductors. Then you have next topic is superconductivity. This is also very simple. So superconductivity, as the name suggests, that a material would attain superconductivity state would be a state where resistance is very less or almost zero. Okay, and almost zero means if the resistance is almost zero, then it becomes a superconductor. Then the conductivity will increase. You know this. Resistance decrease, conductivity increase. You know this. So if resistance becomes almost zero, the conductivity will increase and it will become a superconductor. Very simple. The phenomenon of complete loss of resistivity by certain metal alloys when they are cooled below a certain temperature. So it is achieved under a cooled state. Superconductivity is achieved under a cooled state. The temperature at which the substance undergoes a transition from a normal conductor to a superconductor in a zero magnetic field. So this is important. Right now, you would not be able to understand why zero magnetic field. Next chapter, when you do magnetism, then you will understand why this is so. The temperature at which the substance undergoes a transition from normal to superconductor is a transition or critical temperature. Very simple. So critical temperature is that temperature at which the normal conductor becomes a superconductor. So this next topic is resistance in series and parallel. So first we'll do resistance in series. This is a simple topic. So series and parallel you have understood from the series parallel of capacitor, that topic, series and parallel arrangement of capacitors, you have understood. Then when is a certain combination a series or a parallel? So here also it's the same thing. You see the resistances are connected to themselves rather than they are all connected to the cell. So if the resistances are connected to themselves, they would be in series, and if the resistances are connected across one fixed point, they will be in parallel. So let's discuss about the series. Let's find out what will be the equivalent resistance for a series combination. This you have done in your junior class as well. So this is just a revision. Now you know that potential drop across this each resistance will be V1, V2, and V3. V1, V2, V3, and according to the Ohm's law, so V1 is equal to I R1. This is also simple. Now current I is flowing in the circuit, and potential V is given by the cell. The cell potential says potential must be is equal to the potential drop across this three, V1, V2, V3. Very simple. V1 plus V2 plus V3. Because again, the total energy that is spent in the circuit must be is equal to the energy supplied by the cell. Obviously, potential difference of the cell there must be is equal to this. And with respect to the cell, V is given a current I, and the cell is assuming the whole circuit's resistance to be one single resistance, that is R equivalent. And this V1, V2, V3 will become I R1 plus I R2 and I R3. So you see that the same current is flowing in all the three registers. In capacitors, we had that the same charge was there in the series. Charge was same in the case of capacitor, but in the case of resistor, the same thing. But here instead of charge, it is current which is same, because the current is flowing. In the capacitor, charge was getting accumulated at the capacitors. In the capacitor's case, charge was getting accumulated. So that's why you consider that the charge will be same in all the series capacitors. But here in this case, current will be same current flowing through all the resistors. So this I current will get cancels off, very simple, and this equivalent resistance then will become R1 plus R2 plus R3. Now, resistance in parallel, again, very simple. Why, how it is parallel, we can identify if the resistances are connected across the same common point. If the resistances are connected across the same common point, then that will be resistance in parallel. So like this. So as we can see here, that these resistance R1, R2, R3 are connected across the same common point A and B. Okay, that means this, all three must have the same potential drop because they're connected across the same point. So same potential drop, that means this V, and this V, the potential drop would be same across them. And because the resistances are different, they have three different resistances, R1, R2, R3, resistance is not same. So the current that is going to flow in each will be different. So we can write this V is equal to, here potential drop will be I1 R1, then again I2 R2 and I3 R3. So to find the equivalent resistance here, we will first see about the current. You see the current which is given by the cell is getting bifurcated or divided into these three. So you can very well say that the current I will be is equal to I1 plus I2 plus I3. And so this I is the current given by the cell. So this I will be the potential of the cell divided by the equivalent resistance, which the cell assume the entire circuit to be one single resistance, is equal to I1. So I1 will become V by R1. Okay, I1 V by R1 plus V by R2 plus V by R3. So V all get cancels, and then your equivalent resistance will become ERQ, and 1 by R1 plus 1 by R2 plus 1 by R3. Very simple. Basic problem related to resistance has already been taught in your junior classes. We will be doing more questions in class then. More complex circuit. This is just a basic introduction, but cell in series and parallel is a vast topic, and there are variety of different types of circuit where equivalent resistance is supposed to be found out, and there are different methods to do it also. But it's easy and interesting topic. We'll be discussing it later.